Hi, this presentation belongs to the course assignments playlist, and in this case it offers you some recommendations on how to start your final coursework. Now, after watching this presentation, I expect that you will be able to explain the sequence of steps comprised in our test workflow, from the very first step, which consists of writing a new test program, to the last step, which consists of pressing the Run button to execute it in our Nexus 3 board. And I expect that you will be able to explain why we need an Intel Hex decoder function in the Nexus 3 board, which you will be able to choose if you want to implement in hardware or in software. Now, you may recall that the test workflow comprises 4 steps, and the first 3 of them will take place at the PC side. That is to say, it will be at the PC that we start by writing the source code using Notepad++, for example. Then it will be at the PC side yet that we use the TASM cross-assembler to compile the source code to object code. And finally, it will still be at the PC side that we use the hyperterminal utility to transfer the object code into the Nexus 3 board. Finally, the last step will take place at the Nexus 3 board, since that's where we will press the Run button to generate the waveforms at the test access port corresponding to the test program that we have just written. I guess that the best way to illustrate how this works in practice is by considering a specific example, and what I propose to do in the following slides is to write a small test program to control the LEDs that are present in our demonstration board. Now, please recall that our demonstration board comprises 2 boundary scan chains, and the LEDs are connected to the outputs of the device that is placed in the second boundary scan chain. Since the current set of test commands that are proposed for your coursework does not include one test command to switch from one boundary scan chain to the other, we will have to assume that the appropriate physical connections will have been established beforehand. Now, of course, we might prefer to implement a select test access port command or any other equivalent command that would enable us to indicate into which test access port the following program is to be executed, but I leave that up to you. Please keep in mind that you should revisit the boundary scan slides in order to understand this example, and particularly you shall bear in mind what is the test access port controller state transition diagram, since that is what explains why we need to execute this sequence of TMS commands. Anyway, we will start by resetting the test logic, and so this first command will bring every test access port controller in each device to the test logic reset state. Then if we execute TMS0, that is to say set TMS to 0 and drive 1 clock pulse at the TCK, then this will take us from test logic reset into run test idle. And then by executing TMS1, this will take us to select data register, and so on and so forth until we get to select instruction register. Now, when we reach this state, we will be able to start shifting in the instruction code. And in this case, since the boundary scan devices used in this board have an 8-bit instruction register, this means that we will have to shift in 8 bits. What this command shows is that the bit stream to be shifted in is all zeros, which corresponds to the external test instruction. And since this is a shift and compare command, we will be indicating what is the expected bit stream to come out at the test data output pin from the board. And using an all-one mask indicates that we know that every bit coming out of TDO should be as indicated in this bit stream. Then we can update the instruction register, move on to the shift data register state, and then we will have to shift in 18 bits, since each boundary scan device used in this board has an 18 boundary scan register comprising 18 cells. And this bit stream will set the output pattern as required, that is to say, on, off, and so forth. So the last thing to do is to update the instruction, the data register, and the LEDs will light up as requested. So this is the SVF-like source file that we will have to create in Notepad for this example. And after completing this first step, we will be able to move into the second step of our test workflow, which consists of compiling this source code into object code. And this is where we will use TASM, and if there are no errors present in the source file, then the TASM will successfully generate the listing file, which shows side by side the source code and the corresponding object code. And to the left of the object code, we can also see the address of the test program memory positions where each object code is to be stored. And the object code to be transferred to the Nexus 3 board will have been generated at this step as well. Now, TASM generates the object file in Intel Hex format, and so it is important that we take a more detailed look at this format. Now, Intel Hex is simply a representation format that is used to convey binary information as a text file. So every line, or a record as it is called, starts with a colon character. This is the start code, and it is followed by 2 digits indicating the number of data bytes in this line. Since this is indicated in hexadecimal, this tells us that this data line comprises 24 data bytes. The 4 next digits indicate the start address, where this sequence of data bytes is to be stored. In this case, we are just saying that the first byte is to be stored at address 0. And then the 2 following digits indicate the type of record. In this case, 00 indicates that this is a normal data type. Actually, the last line will be will have 01 in this field, indicating that it is a end of file record. And from this point on, we will have the data bytes. As you will notice that if you look at the object code side by side with the source code, you see that the reset command corresponds to object code A1, and A1 is what you see represented in these 2 positions. Now, actually, this means that we will be sending 2 ASCII codes for this byte A1. The first ASCII code will be for the uppercase A, and the second ASCII code will be for the digit 1. So this means that the data field comprises 2 times n digits to represent n bytes. And finally, the 2 last digits are a checksum representing the 2's complement of all the other fields except the start code. And this checksum is used for error detection purposes, if we wish. So we are now ready to look at step 3 in our test workflow, and this step 3 consists of using hyperterminal or teraterm or whatever utility you prefer to use to send the object code in Intel Hex format to the Nexus 3 board. Now, if you want to learn further details about Intel Hex, I recommend you to visit the corresponding Wikipedia page at this address. And finally, we will be ready to carry out the fourth and last step in our test workflow, which consists of simply pressing the Run button to execute the test. Now, at this point, I would like to call your attention to the fact that this sequence of ASCII codes that we will be receiving in our board will have to be stored in the test program memory, but not all of the ASCII codes that will be received. That is to say, the initial characters will not be stored. We will get a sequence of ASCII codes that starts with hexadecimal 3A for the colon sign, then hexadecimal 3-1 for digit 1, 3-8 for digit 8, and so on and so forth. But all of these initial characters are to be discarded because what we want to store in the test program memory is simply the object code in hexadecimal format. So what this means is that the initial sequence of ASCII codes to be received is to be discarded, although we will have to use some of this control information, such as the address where the sequence of object code characters is to be stored. And then when we get to the object code representation, we will receive two ASCII codes for each byte to be stored in the test program memory. And this means that we will have to receive the first ASCII code, wait for the second ASCII code, then compress this information into the appropriate byte to be stored in the test program memory. Taking the example of the first object codes shown in this line, we will get 4-1, which is the ASCII code for uppercase A. Store this information temporarily, and then we will receive 3-1, which is the ASCII code for digit 1, and we will have to combine these two ASCII codes into the A1 byte to be stored in the first position. And the same happens with all the other ASCII codes for the remaining object code characters. So what this tells us is that we will need to implement an Intel Hex decoder function, and that can be done in hardware or in software, but it will have to be done. Actually, you might store the Intel Hex sequence directly in the RAM module, but in that case you would anyway have to decode it at runtime, so there's no point in doing it. And of course, there would be a waste of memory space. I actually invite you to calculate what is the percentage of that waste. So what I recommend you to do is you could start by drawing an ASMD chart for the Intel Hex decoding function. And once you have this chart, you can write the implementation code, be it in VHDL if you want to have a hardware decoder, or in whatever software language you are using, assembly or C or whatever, if you want to write it in software. Whatever way you decide to do it, I recommend that you do it as soon as you go on receiving the characters, and that you validate your implementation by simulation before continuing with your development work.